So we just finished talking about quadratic functions. And quadratic functions are polynomials of second degree. So now we're going to talk about polynomials of higher degree, which is third order polynomials, maybe fourth order polynomials. And most of the stuff that we've done applies here. We don't have vertices anymore. We have what are called local maximums and minimums, possibly. We'll actually have to wait till calculus to be more specific about those points on the curve. But we're interested in the x-intercepts. And for a second order polynomial, quadratic, we either have 2 or we have 0 x-intercepts. For polynomials of degree 3, we have at least 1 x-intercept, or we may have as many as 3. So we also have one y-intercept. We always have one y-intercept for functions because functions only have, for each value of x, there's only one value of y. We have something called end behavior, which is whether the function, as you go to positive infinity x or positive infinity y x or negative infinity x, that whether it goes to positive or negative infinity. So in third order polynomials, it doesn't. The ends don't go the same direction; they go opposite directions. So the question is, how do you find the x-intercepts, or what we would call the roots? And that is a little more difficult sometimes. When you have a quadratic equation, you can use completing the square. You can use quadratic formula. You might, if you're lucky, it might be something you can just do by inspection. Okay, so here's the basic things. Use the leading coefficient test to tell us about the end behavior. Look at the zeros, which are the x-intercepts. How do we sketch those? And then we're going to talk about the intermediate value theorem. What that basically means is that because the function, the range goes from negative infinity to positive infinity, or from positive infinity to negative infinity, we know that for a third order polynomial, it'll take on every value. So the domain is all real numbers, and the range is also all real numbers, and has to cross the x-axis somewhere. Okay, so the leading behavior, leading coefficient test. So what I wanted to do here was to just demonstrate these two things. This is a function x cubed and the function x cubed minus 2x squared minus 5x plus 6. So let me just copy this over, which is just the two functions that I'm really alluding to. So let's graph that. And let me zoom out in the y direction. Okay. So when you're close to x equals 0 or y equals 0, they don't match up very well. But as I zoom out further in the y direction and the x direction as well, you can see that they tend to approach each other. They get closer, relatively speaking. They don't ever equal each other. But zooming out, you can hardly see that there was that difference around the origin. So this is what's called end behavior. It means that for both of these functions, that as x gets larger and larger towards positive infinity, that these two functions are going to end up approaching positive infinity. And then on the other side, as you take x and you go the other direction to negative infinity, the y values are going to go to negative infinity. And so a third order polynomial starts out down here. Whoops, didn't mean to do that. So they start out approaching negative infinity on this side and then going close to 0 and then positive infinity. Now if you change the coefficient to be a negative number, so you have negative x cubed, what happens is, it looks very similar except they're flipped around. So here as you go to negative infinity in x, you go to positive infinity of y, and the opposite. So all you have to do is look at the sign in front of the highest order term, and that'll tell you which way it's going. So let's just write out the basic rules here for leading coefficient. Okay, if the sign in front of the x cubed term is positive, then as x goes to negative infinity, y goes to negative infinity. And as x goes to positive infinity, y goes to positive infinity. If the sign in front of the x cubed term is negative, then it's exactly the opposite. So we can say then, as x goes to negative infinity, y goes to positive infinity, and as x goes to positive infinity, y goes to negative infinity. So here they go in the same direction, up. These go down to the left, up to the right. These are opposites. So that's all there is to it. So that's for a third order polynomial. Now, and actually this applies not just to the third order polynomial, but it applies to any polynomial with an odd highest power. So x to the 5th, x to the 7th, x to the 9th, x to the 211th. As long as the exponent is odd, then the sign in front of the highest order term tells you what's going to happen. Now, if you have an even function where the highest order term is an even number, like in this case x to the 4th, what I have here is just x to the 4th in general, and then I have x to the 4th with all this extra stuff on there. So let's plot that out and see what that looks like. And we should get two graphs. And again, looking closely, it looks about the same, but what we're going to do is we're going to zoom out a little bit in the y direction, and a lot. I mean the x direction, and a lot in the y direction. So again, you can see that as x becomes large in the positive direction, then y becomes large in the positive direction. And likewise, when x becomes large in the negative direction, y becomes large in the positive direction. So it's kind of like a parabola, except near the origin it has this more interesting behavior, but it's still kind of like, like a cup or something. So now if I change the sign in front of, so if this is negative x to the 4th, and put a negative out in the front there, so now the sign in front of the highest order term is negative, then they point downward. So what's the rule there? So I'm just going to use the same thing, just change a few things. So and we'll just look at x to the 4th, but this applies to all even. So if the sign in front of the x to the 4th term is positive, like over here, then as x goes to negative infinity, y goes to positive infinity. And as x goes to positive infinity, y goes to positive infinity. If the sign in front of the x to the 4th term is negative, then they both go the same direction, which in this case is negative infinity. They point downward. So whether you're going to negative infinity or positive infinity in the x direction, the y behavior ultimately is pointing down. So this is like point up, this is point down. Okay, the next thing we're going to talk about is the zeros of polynomials. And what the zeros are the numbers that make the polynomial equal to 0. The y value is 0. So when you calculate the zeros of polynomials, you're also calculating the values, the x-intercepts. So it's basically the same thing. So I guess you can say the zeros are x values where the function equals 0, and so are the x-intercepts. That's where the function is 0. So they both have the same, they're tied together like that. So if you have, depending upon the order of the polynomial you're going to have a maximum number of factors. So if you have a third order polynomial, you can end up with 3 real factors. The factors are x plus or minus some number. Once you know the factors, then you can figure the zeros are going to have an opposite sign to, if you set x minus something equal to 0, then x is going to be equal to that number. You'll see that later. If you have a fourth order polynomial, you can have as many as 4 x-intercepts or zeros. Now for third order polynomials or any odd ordered polynomial, you'll have at least 1, but they always have to become an odd number. So if it's a third order polynomial, you can have 1 0 or 3 zeros. If it's a fifth order polynomial, you can have 1 0, 3 zeros, or 5 zeros. Likewise, with fourth order polynomials, there you can have 0, 2, 4, 6. So these are always, here you had 1, 3, 5. Here you can have 0, 2, 4, 6. So this example we had here, if we zoom in, you can see that the red one actually has, which is just y equals x to the, well, that was y equals negative x. Let's make it positive, back to positive. So make the positive, then make that one positive. Graph the thing. Okay, now let's flip the other way. X to the fourth has what, 1, 0, which is when x equals 0, y equals 0. The other one has 4. You can see it has 4 intercepts, or 4 zeros. So quadratic can have 2 zeros, 2 x-intercepts, or you can have 0. If I added 20 to this, it would move it up and make it so you didn't have any x-intercepts. Or you might, if the parabola is like this, then you have zeros, but they are complex, meaning there's a real and an imaginary part to them. Knowing the complex roots doesn't help you find anything as far as graphing is concerned, because graphing is only dealing with real stuff. Now, third order polynomial, in this case I have 3 x-intercepts, I have 3 real zeros. If I shift this thing up so that it only intersects one place, that means I have 1 real 0 and 2 complex zeros. So you always have an odd number of zeros, and you always have 2 complex. You might have one real and 2 complex. You might have 3 real and 2 complex. You might have 1 real and 4 complex. So there's always an even number of complex roots. Here's a fourth order polynomial. So there you could have 4 real roots where it intersects 4 times. You could have 2 real roots and 2. So here's the case where you have 2 real zeros. And there you have 2 real zeros and 2 complex zeros. Or if I moved it here, I have 2 real zeros and 2 complex zeros. Here I have 4 complex zeros. There's no real zeros because there's no x-intercepts. Okay, so what does this say here? Odd order polynomials have at least one real zero. Okay, we've said that before. The real zeros of polynomial functions. If f is a polynomial function and a is a real number, the following statements are equivalent. Okay, so there's just different ways of saying the same thing. So we're saying it has 1 0, or there is 1 0 where x equals a. So we're saying if we say x equals a is a 0 of the function, we can also say that x equals a is a solution to the polynomial equation where you set the function equal to 0. You can say x minus a is a factor of the polynomial. Or you can say that a comma 0 is an x-intercept of the graph of the function. So to have those satisfied, if you have one satisfied, they're all satisfied. Okay, now you can have repeating zeros. So it says a factor x minus a to the k power, where k is greater than 1, yields a repeated 0 at x equals a. So this is a real 0, but when you factor the function, you have the same 0 twice. So let me just give you an example of that. I may have it on the next page, but let's just do it while we're thinking about it. So here's the factored version of the function x minus 2 squared times x plus 1. So this has 3 real zeros. One is x equals 2, the second one is x equals 2, and the third one is x equals negative 1. So you can see, because I did that twice because I've got x minus 2 squared, or I could say it's x minus 2 times x minus 2 times x minus plus 1. Now the special thing about when you have repeating zeros, then you have it where the graph touches the x-axis. So this has a x-intercept that's happening at 2, and then we have an x-intercept 1. So the function is probably going to look like this. Comes up through this, and then when it comes back down, it doesn't actually go through, just goes like that. So that's the consequences of a repeat 0. That says if k is odd, the graph crosses the x-axis. Okay, so what does that mean? Well, if I did f of x equals x minus 2 cubed times x plus 1. So now I've got 4 zeros. So this is going to be a 4th order polynomial. So let me draw a graph. Just going to make it very, so again, there's going to be a 0 at x equals 2 and a 0 at x equals 1. Now, because this is a 4th order polynomial, because I've got x cubed times x, I know that it's going to come this direction. So what it'll do is it'll come through here. Because this is a negative 1, x equals negative 1, it's a single 0, it goes straight through. Then when this thing comes back around, it'll go like this, and it'll go something like that. And that's because this is odd. So it's still unusual because it doesn't just go straight through like this one goes straight through. Here it comes up and it kind of levels off, and then it starts increasing again. So it increases. That's probably not the best drawing there. So it comes up, and it then goes, what we'd have say is 0 slope here. So again, if it has even repeat roots, then it comes down and touches it. Doesn't actually go all the way through. If it's an odd repeated root, then it does go through the axis, but it does come down, and the increase slows down to 0 and then goes again. Okay, so now we've we talked about zeros. The rules for sketching a polynomial function is first you apply the leading coefficient test, depending upon whether it's an odd function or an even function, whether the sign in front of the highest order term is positive or negative. Then you find the zeros of the polynomial. And sometimes you have to pick a few additional points just to give you enough information. Sometimes finding the zeros as well as the y-intercept are enough to give you a pretty decent drawing. Sometimes you just don't, maybe you don't have any x-intercepts. Then you have to choose some other points somehow or another. Now, up to this point, we're going to assume that the zeros are reasonably easy to find. In subsequent sections in this chapter, we'll look at how to approach figuring out the zeros of third-order polynomials. How do you come up with those kinds of things analytically? Okay, so here's our first example: x cubed minus 9x. So it's a third-order polynomial. It's going to have 1 or 3 real roots. So we're going to need to factor this, which is not that bad because if we factor it, we have a common factor of x. So you get x times x squared minus 9, and then you could factor that. It'd be x plus 3 and x minus 3. So that's the factored version. We'll come back to that. We actually come back to it here. But first thing we do is, what is the leading coefficient? Well, what is the highest order term? Well, it's x cubed. What's the coefficient? 1. What's the sign? Positive. So it's positive. It's odd because this number is odd. So what that means is, in general, it's going to start out here at negative infinity. As you go from left to right, it'll come up. It may loop over like that. It may, but we do know that the end is going to start out down here, and this end's going to start up there. Now, we need more information to figure out what's going on in between. So to do that, we set the function equal to 0, and you factor it, which I've already done, so I'll just repeat that. So it says find the zeros of the polynomial, but if you remember back, to find the x-intercepts, we set the function equal to 0. So it's the same thing as if we wanted to find the zeros. If we find the factors, we find the zeros of the polynomial, we find the x-intercepts. Okay, try to see what I got here. Okay, so what we find is that when any one of these three terms is equal to 0, then the function's equal to 0. 0 times anything is 0. So what you do is you set each one of those individually equal to 0 and solve for x. Well, the first one's easy because it's already solved for x. The second one is x plus 3 equals 0. If you solve for x, you get x equals negative 3. And the third one, x minus 3 equals 0. You get x is equal to 3. So those are my x-intercepts. So it would be 0, 0, negative 3, 0, 3, 0. So those are the points on the graph. Now what am I doing down here? So the next thing is plot a few additional points. So I've got the zeros. So the best thing to do is to pick a point that's not the ones that I've already done. And so what I did was I divided my domain from negative infinity to positive infinity into four intervals, and I chose a number just outside of those intervals, just near the x-intercepts or between the two. So since I go from negative infinity to negative 3, that's the most negative interval. Negative 3 to 0, negative 3 to 0, 0 to 3, 0 to 3, 3 to positive infinity. I'm going to pick numbers just a little bit more negative than negative 3 and a little bit more positive than positive 3, and then pick numbers right in the middle. So if you evaluate the functions at those values, so I just plug these numbers back into the original function to find the y value, you'll see f of negative 4 is negative 28, f of negative 1.5 is 10.125, f of 1.5 is negative 10.125, and f of 4 is 28. You can kind of see a symmetry there. So now we just draw the graph. So here is some graph paper. And let's just put a scale in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is negative 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's positive 10. Now, in the y direction, you can see my y values. I've got negative 28, positive 28. So what I think I'll do is I'll say every 2 marks is 10. So this is positive 10. Go 2 more, that's 20. 2 more, that's 30. 2 more, that's 40. Do the same thing in the other direction. So that's negative 10, negative 20, negative 30, negative 40. Okay, so that's my scale. Now let's plot. We'll use the end behavior once we've plotted a few things. So our zeros were x equals 0, so you can see the red dot there. X equals negative 3, x equals positive 3. Now, we can then take these additional points that we have here, negative 4, negative 28. So 1, 2, 3, 4, that's negative 4. Negative 28 would be, here's 30, here's 20, so 28 is going to be about right there. Then negative 1.5, which should be about right there. We've got 10 point, a little over 10, so that's right there. So it's negative 1.5, positive 10. Then we got positive 1.5, negative 10-ish. And then at 4, 1, 2, 3, 4, positive 28, which is right here. And you can see the end behavior here kind of just has to happen because, you know, nothing's going to cause this thing to come back. So it's going to go through that point, through the x-intercept, through this point between the x-intercept, first 2 x-intercepts down this way, through this point here, loops back up, goes up through this point, and continues going. So that's our plot. 3 x-intercepts. The y-intercept was 0 because if you set x equal to 0 in the original equation, then you get 0 cubed minus 9 times 0. So that's the y-intercept. So it's also the one of the x-intercepts. Okay, so that's pretty much it for section 2. We're going to do a lot more of this, so don't think that's the end of it. Right now we're dealing with numbers things we should be able to factor without thinking too hard about it.